Hello, everyone. My name is Tong Wang, and I'm a postdoc at the Behavioral Economics group at Erasmus University Rotterdam. So feel free to interrupt me for clarifying questions in the middle of my talk. So the whole world now is curious about the outcome of an event that's going to happen in less than 10 days from now. But don't worry, my talk won't be about politics. What I want to talk about is how we can do forecasts on such an event. So other than polls, the most prominent method for forecasting such a political event is the prediction market. And there are dozens of academic papers in the last 20 years looking into the performance of these markets. So generally on the prediction market, we're interested in a given event that will or will not happen in the near future. 1 unit of the asset on the market will pay out $1 if the event comes true, and 0 otherwise. So anybody on the market can choose to buy or sell the asset at the current price. If people are rational, then they should buy the asset if their belief in the event's probability is higher than the current price, and sell otherwise. The prices rises and falls as the trades go on, and the balance point represents people's consensus about the event's probability. So we see that prediction markets have 2 nice properties. First, there are transparent incentives. People have to put the money where their mouth is by buying or selling the assets according to their true belief about the event's probability. How you can gain or lose money is super easy to understand. Second, the market also aggregates people's opinions. Many papers looking into the accuracy of these consensus probabilities generally found that they are well calibrated. So prediction markets are also used by companies to forecast company performance and external events. So this very nice RES paper in 2015 documents 3 corporate prediction markets and have found that prediction markets involving all the employees can even outperform the experts predicting company performance. So recently, prediction markets are also playing a role in solving the replicability crisis in scientific research. So these are all very promising applications of prediction markets, but all of the events have to be verifiable soon in order to pay out the shares and to effectively incentivize people. So this is very limited. What if the events are unverifiable? So sometimes for policy making, we wanted to know people's beliefs about counterfactual events. And these are, by definition, don't have a chance to play out. And also, for some questions, we're interested in things that we don't know when we will know the answer. For example, just as a quick example, do aliens exist? We will never know when we will find out the answer to that question. And sometimes we're interested in events that are far away from us. For example, governments managing huge projects that cost billions of euros and span over 10 years. They want to know how things are going now so they can see whether the planning needs to be improved. So in all of these cases, how can we still organize a market where incentives are transparent and opinions are aggregated? So the paper that I'm presenting to you now solves this problem. We propose a mechanism called the Bayesian markets that extends prediction markets to unverifiable events. And it is a joint work with Aurélien Balion and Benjamin Tariq. So I want to convince you through my talk that for binary questions, Bayesian markets preserve the 2 properties of incentivizing and aggregating, and the incentives are transparent and easy to understand for people. So I'm going to talk a bit about our contribution of the paper here and where do we stand in the literature. So we are definitely not the first one to solve these problems. So for how to incentivize people on verifiable truth, there is many scoring rules invented, such as the Bayesian truth theorem and a whole literature on peer prediction. So, but if you look at all of these scoring rules, you would realize that none of the people will understand all of the complicated equations. It is very complicated how to score people. And there's no way you can communicate to subjects in an experiment or in a market actually how it works. And another paper by Ballion 2017 first introduces the concept of Bayesian markets. And our paper now actually builds upon his concept of Bayesian markets. We adapt the original design and try to say that it preserves the incentive property. So the literature on incentivizing unverifiable truth now, we can only incentivize binary. We can only incentivize basically people's opinions, but not probabilistically, which is why if we have a report on people, which answer people think is true, then we also face the aggregation problem of which opinion to select if opinions disagree. So there's another paper in 2017 called the surprisingly popular algorithm, and they also solved the problem. But we want to say that we are the first paper to kind of solve the two problems at once, and also present a very easy to understand market for participants to review their private information and to aggregate their opinions as a single opinion in the end. All right, so are there any questions so far before I go into the details of how the market works? Everything clear on what we're trying to solve here? All right, so I'm going to move on to how the Bayesian market works. So the mechanism works like this. So let's say the center is interested in a yes or no question. And we have a bunch of agents that has some knowledge about the yes or no question. And the center and each agent can trade an asset on this market. The settlement value of the asset will equal to the proportion of other people answering yes to the question. And for each agent, if you answer yes, then you can buy the asset at a random price determined individually. And if you answer no, then you can sell the asset at a random price. After you answer yes or no to the question, a random price will be drawn, and you will be asked about your willingness to trade, whether you want to buy or sell the asset at this random price. We have a trading rule that if there's another person who's willing to take the opposite bet, then your trades go through and you would get the payoff, and otherwise you would have no trade. So this is how the Bayesian market works. And in this talk, I'm going to focus on basically explaining to you the intuition of why the Bayesian market can solve these two problems. And I want to focus my theoretical setting on the infinite population case, because I think that shows the intuition the best. And in a large part of our paper, we try to deal with finite population. We try to say that our results for infinite population also extends to the finite case at the limit. And we also have simulation results that shows how large the group needs to be and how good is the performance of our algorithms for finite population. So now I'm going to go into the theoretical setting for infinite population. It is a very simple one. We basically use the same framework as the Bayesian truth theorem or the surprisingly popular or the original Bayesian market. And it is very standard in the signal detection literature. So suppose that we have two states of the world, the yes world and the no world. And we assume that the proportion of people answering yes would be higher in the yes world than the no world. And here we don't assume anything about whether omega y and omega n is larger or smaller than 50%. So we don't assume that the majority of the people is correct here. So that's, and people have a common prior before they receive the private signal about what's the probability of each world that we're in. So before you receive your private signal, you would think the average or the expected proportion of people answering yes would be somewhere in the middle between omega n and omega y. So after you receive a yes signal, so let's say you think that the answer to the question is yes. So then you would increase your prediction of the proportion of people answering yes through Bayesian updating. basically using your signal as the to deduce the state of the world. And after you receive a no signal, then you would downwardly adjust your expectation of the proportion of people answering yes. So remember that the Bayesian market, in the Bayesian market, if you answer yes, you can buy the asset at a random price. So because for people answering yes, they receive the yes signal. So their reservation price for this asset would be their expectation of the proportion of people answering yes, which is omega 1 bar here. And for any price that is lower than this reservation price, they are willing to buy. And symmetrically, if you answer no, then your reservation price is omega 0 bar. And for any price larger than that, you are willing to sell the asset. So here we see that within this range of omega 0 bar and omega 1 bar, there will be trade. The buyers are willing to buy and sellers are willing to sell in this case. And we can see that if all the other people are telling the truth, then you also have the incentive to tell the truth in order to make a positive profit on the market. And we show that truth telling is a Bayesian-Nash equilibrium here. So that's the incentive property of the market. And if we go one step further, if we are on the yes world, then we know that omega y percent of the people will answer yes. So in that case, because trades happen in the middle here, so we will know that in this case, buyers would make money because the asset value is actually higher than the price that they are buying the asset. And if we're in the no world, then we say that we can see that sellers will make money. So here we propose theoretically this follow the money in Bayesian market. We can aggregate people's opinion by looking at who makes money. If buyers make money, then we know that we're in the yes world. If sellers make money, then we know we're in the no world. So as I mentioned before, there's another recent algorithm called the surprisingly popular algorithm, can also solve the aggregation problem. So what they do is we use the exact same theoretical setup, but for them, they ask people directly about their prediction of other people answering yes. So the average prediction would end up somewhere in the middle. And they say that if the answer yes is surprisingly popular than what people on average think, then yes is the correct answer, and otherwise no is the correct answer. So to summarize a bit the intuition of our model, if we think about how to aggregate opinions, if we use a majority rule, we are basically making the assumption that omega y and omega n are on opposite sides of 50%. We always assume that the majority of the people can answer correctly. And for the surprisingly popular algorithm and our follow the money algorithm, we don't assume this 50%, but we deduce where the threshold should be based on what people would predict and on what people would bet. So this is how the aggregation property would work. So I finished the theory part of our algorithm, and of course we want to move on from theory to the lab experiments to see whether our algorithm works or not. And we face some challenges. So for empirical data, we can imagine that people would make mistakes, and there are a lot of noise around what they report. So in the theory, we only have two types of agents. Everybody would have the exact same reservation prices and would make perfectly rational decisions. But for empirical data, it's unlikely to be the case. What we do in our first empirical algorithm is we compare the average profit for buyers and sellers. So in the theory, only one side makes profit. But in the empirical data, it could be that some buyers make money, some buyers lose money, and we just compare the average profit for two sides. And for small group sizes, we can also imagine that sometimes no trade would happen. In that case, we wouldn't have any profit data to use this FTMA algorithm. But that doesn't mean that people's betting decisions and people's reporting doesn't have any information. And how we deal with that is we propose a FTML algorithm. We first estimate the reservation prices from the binary betting decisions, and then we use the theoretical profit to predict which answer is the correct answer. And how it works is basically for each side, for buyer side, for everybody, we know that at this price, whether they decide to buy or not. And then we assume that the probability that somebody decides to buy at a certain price, given that they report yes or no, is a logistic function based on the distance of the reservation price and the random price that we're asking. And then after imposing that omega 0 bar is smaller than omega 1 bar, we use the maximum likelihood estimation to fit the data and to extract the reservation prices from the betting decisions. So these are the algorithms that we propose for empirical data, and we're going to use these two algorithms in our experiment. And so I want to talk a bit about the goal of our experiment now. So of course, we didn't go immediately into forecasting real-world events, because in order to evaluate our algorithm, we need to know the ground truth. We need to know what is actually the truth, and then to compare our prediction with that. And we thought there will be a lot of challenges around that, because sometimes the truth is unverifiable, so we cannot know what truth there is. And we also want to know more about the underlying parameters and in the environment. So what we thought is we will design an experiment, control all the elements in the environment so that we know the underlying data generating process, we know the ground truth. And then we ask people to participate in the market to see whether we can deduce the truth. And the task we come up with is a very standard one in economics. We use the urns and balls. And in this case, the two states in our model corresponds to the urn left or urn right. We can see that urn right, let's say, is the yes world. And in this case, there are more yellow balls than urn left. So we tell the subjects through an introduction video that there are two urns, and one urn is selected, but we won't tell you which one. And there are 100 participants in your group. We will distribute the 100 balls in the urn to the 100 participants. And you will only get one ball, and you will only get to know the color of your draw. And after that, you have to predict which urn was selected and to also bet on other people's decisions. So this is how our follow the money Bayesian market treatment looks like. After you get to know the color of your draw, then we ask you which urn do you guess was selected. You have to report either urn left or urn right. And then we ask, do you bet that the number of participants guessing a certain urn is at least a random price? And you just answer yes or no. So very simple binary questions here. In order to compare our algorithm performance to the state of the art in this literature, then we also have a surprisingly popular algorithm. After people report their guess, we simply ask them, how many participants do you predict to have guessed right? And people have to input a number for their prediction. So if you compare the two treatments, you realize that our Bayesian market treatment uses less information because we only have binary information. And here people have to report a specific number for their guess. For implementation details, we did an experiment on Prolific. We have about 900 US students. And there are 30 situations in total with different parameter combinations of omega y and omega n. And each participant faced 15 of these situations. Okay, so let me quickly show you the results. I first show you how we deal with the incentives problem. On the left here, I plot the FTM payments versus how many of the guesses, how many of the guesses are Bayesian guesses. So here I define Bayesian guesses as if subjects predict according to their signal, then they would be labeled Bayesian guesses. And here we see that the more you're rationally reporting your guess, then the more payment that you earn. And on the right side, I plot the number of ex post corrected guesses. So here, of course, nobody has an expertise in knowing which urn was selected, but you could get lucky by getting more signals that are corresponding to the actual urn that was selected. So we see here that the more correct ex post guesses you made, the more payments that you get in the end. So here we show that our market incentivizes truth telling and reporting. And for the aggregation problem, we simply look at the accuracy of prediction. After we use our two algorithms, we compare that with the ground truth. And this is the number that you see here. We separate our 30 situations into two clusters. The first cluster would be the cases where majority rule assumption would hold. So omega y and omega n would be on opposite sides of 0.5. And we see here that the majority rule performs very, very good. Over 95% of the case, just by simply following the majority, we can deduce which urn was selected. And we see that our FTM-A algorithm, simply by looking at the average profit, doesn't perform that well. But for our logistic regression algorithm, its performance is the same as the surprisingly popular algorithm, even though we use less information. And for the other cluster of questions that majority is not necessarily correct, we see that the majority rule indeed performs just like a coin toss around 50%. And we see that F surprisingly popular and our logistic algorithm can significantly improve upon the majority rule. We also show through simulations using our data that for different group sizes, it seems that our logistic algorithm can also learn better as the group sizes increase more. All right, so to briefly summarize and to conclude, we show that the Bayesian market has very transparent incentives. As a subject on the market, you only have to report your guess for the question, and then your bet, whether you want to bet or not on other people's actions. And in theory, we show that it works perfectly under reasonable assumptions. And in practice, we also develop two algorithms to extract information from empirical data. And we show that our logistic algorithm can perform really well, even though it uses less information than the surprisingly popular algorithm. All right, so this concludes my talk. I'm looking forward to the discussion and also to any questions that you have. Yeah, thank you.